Slight correction. Thank you very much for the introduction. That's the first time I've ever been called Batman, I think. Slight correction, I'm not going to talk about Mali CPUs, I'm going to talk about the ARM processor CPU itself. Other people far more expert than me on Mali are going to come and talk about Mali later. I'm a CPU guy. There's a little bit of information about me. I did physics and computer science and then software and then I trained people and now I manage training people. But it's great to take part in days like this to actually come out and tell people about ARM technology, which is something I'm moderately obsessed with and something I think is incredibly cool. There's a bit of a history of ARM. It doesn't go all the way back. Not quite. We actually celebrated ARM's 25th birthday yesterday. The birthday itself was last week. We celebrated the birthday yesterday, and I can see just in the room there one of these incredibly cool limited edition, once only ARM at 25 t-shirts in that fantastic, vile colour. So that, yeah, you see a few more of those if you come up to our offices in Cambridge. There's certainly a lot of people wearing them yesterday. But that history goes back to one particular product here, dates from 1995, the ARM 7 TDMI, which you may or may not have heard of. If you're as old as me, you'll definitely have heard of it. That processor there is primarily the reason that ARM is most associated with smartphones. It was the first runaway success processor core that ARM produced, say in 1995, and it went into two phones that took the world by storm. The banana phone, remember that one, the Nokia 8110, or 6110, which was the phone that Neo used in The Matrix, oddly enough. And it went into this one here, which is the Nokia 5110, which was the first phone to introduce the world to the game Snake, if you remember that. Both of those were absolutely massive successes and really kick-started ARM's penetration into the mobile phone industry, and that drove the company for several years after that. And we've, as Nizar has explained to you, we've diversified into all kinds of sectors ever since then as processing requirements go up and new application areas open for us. But it all started really, say, back in 1995 with the ARM 7 TDMI. I could quite happily talk about that slide for 2 hours, but I'm not allowed because I've only got half an hour. But what I want to focus on is the kind of green box over on the right, which is the latest version of the architecture, ARM v8. All our architectures are evolutionary. ARM v8 is the first one to introduce 64-bit capability into the processor itself. It is true at the moment that 50% of smartphones shipping already have 64-bit capability, and it'll be based around an ARM v8A processor core. So that's now. In 2 or 3 years' time, it'll be 100%. But the penetration of 64-bit into the mobile space has been incredibly fast. It's taken, it's torn through the industry very, very quickly indeed, and it will keep on doing so. So if you haven't sort of got your head around ARM 64-bit processing, then it's something that I would encourage you to do. You really need to do, because there are lots of goodies in there which you can leverage to get a lot of extra power out of your device. And Nizar's touched on 1 or 2 of these things. And I've got 3 areas that I want to talk about. One is the 64-bit processor capability itself. The second is multi-core, and especially that big.LITTLE processing, which is something that you can really leverage to get a combination of high processing power and high energy efficiency, which is very important for a mobile device. And the third thing I want to talk about is just introduce you to the SIMD instruction set that we have. It goes under the brand name of Neon. And that's a very, very powerful instruction set if you can work out how to use it. And I'll give you some simple pointers towards how to use that. But first of all, let me just unpack ARM v8A. There's a lot of new features in here. But one thing, sort of fundamental thing about it is it introduces 2 execution states. A 32-bit execution state called AArch32, which is a horrible name, but the marketing people came up with it, and a 64-bit execution state called AArch64. This one over here, the AArch32 state, is backwards compatible with ARM v7, the 32-bit processors that power almost all smartphones up to today. So that's totally backwards compatible. It will run your binaries from a 32-bit software build. So it's a total evolution from that. There's 1 or 2 extra goodies that we packed in there. There's some crypto instructions. As long as you don't live in North Korea, we can give you those. And there's some extensions to the SIMD capability, some extension instructions in there just to give it a little bit more flexibility and some extra flexibility in the memory model. But it's this half over here that is the focus of today, really, this 64-bit capability, which comes with a new instruction set, a hugely expanded register bank, and a lot of extra very streamlined capabilities. So that's what I really want to talk about today. So 2 execution states. One is backwards compatible. The other gives you access to all that 64-bit capability. The 2 interwork in quite a nice way. We don't have time to go into that hugely, but essentially they share the bottom half of the register bank. So a 64-bit register, X0 for instance, which is a full 64-bit register in A64 state, the bottom half of that is R0 in AArch32, so that the register values can be passed back and forwards between these 2 execution states. And the privilege model and the exception model allows you to implement a very nice stack of applications, operating system, and hypervisor, and then secure software on top of that, all very nicely integrated as a stack, so you can host 32-bit applications under a 64-bit OS. You can host 64 and 32-bit operating systems under a 64-bit hypervisor, and so on. So a lot of possibilities. But anyway, first increased capability is the increase in size of the register bank. V7, the 32-bit state, gives you access essentially to 16 32-bit registers, which was quite a lot back in 1985, but it's not a huge register bank these days. The V8 64-bit state gives you access to 32 64-bit registers. That's a huge increase in working space and headroom, if you like. And the compiler, I'll show you in a minute, the compiler and the ABI allows you to leverage that. But it certainly gives you a 64-bit arithmetic capability natively in registers without having to concatenate registers. So you've got a lot more data processing capability. Obviously gives you access to a 64-bit memory space because all pointers become 64-bit and can be held in single registers. There's a separate register file, which is at the bottom of the slide there. That's to do with the SIMD instruction set, this neon instruction set, and this is an additional 32 registers, which are all 128 bits long. And we can split these into vectors and then carry out SIMD operations on those, and I'll show you a little bit more about that later on. They can be addressed as word size registers, double words, or quad words. Of 128 bits. So there's a lot of addressing capability there and a huge amount of extra working space and storage space. Just an indication of an immediate increase in performance you would get if you take your 32-bit code and just recompile it for 64-bit. Apart from the huge increase in just working space and headroom which your procedures get, this is the changes that we've made to the ABI here. You can pass 8 64-bit parameters in registers into a function. That is 4 times the amount that you could pass in a 32-bit application. You only pass 4 32-bit quantities. Here you can pass 8 64-bit quantities. It's a huge increase in space that you can pass without touching the stack, without having to go to memory, without having to incur all that overhead. And then we can pass back 128 bits of result as well. So there's a lot less stack usage for just through recompiling. And a huge amount here, 19 registers, 19 64-bit registers, which are available for workspace, temporary values, and so on. So a big increase in capability that you get simply by recompiling, and essentially that comes for free. You also get a new instruction set. If you've been working with ARM for a while, you may be familiar with the instruction sets formerly known as ARM and Thumb. They officially have new names now. They're called A32 and T32 to emphasize the fact that both are essentially 32-bit instruction sets that work in a 32-bit programmer's model. And we add a new instruction set called A64. The 64 does not indicate that the instruction encoding is 64 bits in size. It's not. It's still a 32-bit instruction coding. It's fixed length and fixed format. And it's very, very similar in terms of syntax and functionality. Very similar. There's a lot of commonality between a new 64-bit instruction, which is here, and essentially the equivalent 32-bit instruction. So here, this is a 32-bit instruction. It uses a W name, which accesses the bottom half of a register to carry out a 32-bit operation. And that is identical to the equivalent instruction in A32. And it does the same thing, and it works the same way. The A64 equivalent here, we have 64-bit edition, and use the X name that accesses the whole of the 64-bit register, and gives you a 64-bit operation. So if you can read A32 or ARM instructions, you can read a huge amount of A64 without having to turn to the manual. It's very, very straightforward. There's some changes. If you've got heavily into an ARM instruction set, you'll know about conditionality and predication on the instructions. Large amounts of that have been removed in the move to A64 and been replaced with functions, with instructions that have conditional behavior rather than are conditional and predicated themselves. It's quite a complex area, but the compiler makes extremely good use of these conditionally functional instructions. Very nice. And there's a floating point and the advanced SIMD instructions, the neon things, which I'll show you a little bit later, and some optional crypto extensions for implementing common and standard encryption algorithms. Okay, that's what you get simply by switching from your 32-bit environment to your 64-bit environment. You get that huge increase in workspace, a big increase in performance just by recompiling, and that very nice, clean, newly designed A64 instruction set. The other thing that Nizar touched on was multiprocessing. All smartphones these days come with multiple cores, usually a minimum of 4. We've got mobile phone chip developers these days putting 10 cores into a mobile phone, but 8 is very common, 4 is extremely common. Saying 10 is an odd number. I can't work out how they get to that one, but 10 cores is becoming a little bit interesting. So there's parallelism at all kinds of levels. There's parallelism at the instruction level, if you like, these neon instructions, which I'll show you in a minute, which give you parallelism at instruction level through vectorizing instructions. Then common sort of parallelizing programming techniques using standard APIs like RenderScript, OpenCL, and so on. They're available to you, and the OS will make very good use of those. And then multi-threading, which makes use of multi-core if it's available. So how does this multi-core thing work? Well, this is a diagram showing a single-core Cortex A57. Cortex A57 is a 64-bit processor. It's an ARM v8 processor. And if you instantiate it as a single core, it comes with its little private instruction and data caches, little Harvard caches, and it comes with a unified L2 cache, and it comes with a little interrupt controller as well that handles interrupt enabling, disabling, priority and preemption, all that sort of stuff. And it connects externally to an external bus system where the rest of your system lives. Now, if you turn that into a multi-core system, what we call it a cluster, and a cluster can contain up to 4 cores, so you can instantiate 4 of these things in a single cluster. And you can see that each one now comes with its own private instruction and data caches, and it comes with a shared L2 cache that is shared by all the cores in the cluster. The interrupt system extends across all 4 cores, so it allows us to route interrupts dynamically or statically to any or all of the cores symmetrically or asymmetrically. And you see a new piece of magic logic here called a Snoop control unit appears. And the Snoop control unit simplifies the software task massively of managing data coherency across these cores because they have separate caches. Obviously, you've got a data coherency issue, which is going to pop up sooner or later. The Snoop control unit, provided you configure it properly and turn it on, essentially manages L1 data coherency automatically in the background, entirely transparently, so that in software you don't have to keep track of who's got the latest copy of my variable, or where is the latest copy of this particular data item, or who's just changed my data. You don't really have to worry about that. The Snoop control unit migrates data from one cache to the other, automatically invalidates things, automatically preloads things, and so on. It's very, very clever. If you want to know more about that, we don't have time to go into it today, but Wikipedia is very good on it. The protocol you want to look up is called MESI, M-E-S-I. Just go and look that up, and there's some very nice pages there. But we can go further than that, and this is typically what you find in your average smartphone these days, is multiple clusters of cores. So we've got up to 4 Cortex A57s, that's what I showed you on the previous slide, all running as a single coherent system. It's all data coherent, managed by that Snoop control unit, which fits in there. And we've got another cluster here of Cortex A53s, and I'll show you the difference between 57 and 53 in a minute, because the difference is quite crucial. But we can connect these clusters together using a coherent interconnect that then makes all of those up to 8 cores run as a single data coherent system. So you can run one instance of an OS across all of those 8 cores and have them run as a single symmetric multi-processing system without having to worry about all those coherency issues in software. The hardware basically handles it all for you. It's not free. There is an overhead associated with it, but essentially in software terms it's transparent, which is very, very nice. So the difference between 57 and 53 buys you something very, very important. Here, for example, are the pipelines of 53 and 57 in a sort of very high-level overview. And you can see the Cortex A53 pipeline is essentially quite simple, for some value of simple at least. It's about 8 or 9 stages, 10 stages I think. It's simple, it's in order, it has very limited dual issue capability and 3 back-end pipelines. It's a fairly simplistic pipeline for a processor of that complexity. That's because the A53 is a design focused very tightly on energy efficiency. So it's a high-performance core, but it's implemented in such a way that it has a very, very high energy efficiency. The A57, on the other hand, the pipeline of that is a real monster. I gave up counting the stages, it's 20-odd stages. And you can see it's got 5 back-end pipelines. There's an awful lot of prediction going on here. It uses register renaming, multiple issue, out-of-order completion, all kinds of interesting techniques to maximize throughput through the pipeline, because the A57 is focused on best possible performance. It's still energy efficient, yes, but obviously less so than the A53 because it's focused on maximum performance. So it gives you much, much higher performance than the A53 at the cost of some energy efficiency. A53 gives you maximum energy efficiency at the cost of some performance. So when you build a system like that one using 57s and 53s, the OS and the power manager in the system has huge flexibility in moving tasks off an energy efficient core, for instance. When you need some more processing power, it can migrate the task automatically, transparently at runtime onto a high performance core, power that core up, run it for a while, and when that task is finished, migrate the task back to the high energy efficiency core and then power this one down. So it gives you a huge amount of flexibility, and all of that is handled transparently in modern versions of this is the Linux kernel here. There's a bunch of patches under the name Global Task Scheduling, GTS, which implement big.LITTLE MP, big.LITTLE multiprocessing. And all of these, say, are hosted in Linaro. They're developed by ARM, but they're hosted by Linaro. They're standard patches and extensions to the Linux kernel, to the Linux scheduler. And all of the little CPUs and all of the big CPUs are available to the Linux kernel for use when scheduling tasks. So they can take any task and schedule or allocate it to any particular processor at any time. And a task running on one processor can be migrated in real time, transparently, from a little core to a big core and then back again. So you can see where you get that huge flexibility. This is a neat little animation, which I confess I didn't draw, showing that as the system starts, we might power on some little cores one by one. We might start with just one, and then as we run more and more tasks and we start to fill these cores up, we power some more up, and eventually you get to the point where one of these threads, or perhaps a new thread, needs some high processing power, so we power up one of the big CPUs and start moving tasks onto it. And the operating system will handle all of that for you, and it will start migrating tasks on demand onto big CPUs, and those big CPUs will get turned on for you automatically, initialized, and then have tasks shoved onto them. When those tasks finish, or start to reduce their processing power, again, the OS scheduler can automatically migrate them back down here. And if it migrated some more of these over, then it can start turning these big CPUs off, and it can start saving you energy. So you can see how this balance between processing power and energy efficiency is managed, say, transparently by the OS. So developing for this, provided you can parallelize your compute tasks efficiently and carefully and cleverly, developing for this is really quite easy. Our advice is simply trust the scheduler. We've worked on it for quite a while, as have lots of other people. It's tried and tested, it works very well, and it will automatically schedule for performance and efficiency. On any particular device, the kernel scheduler needs essentially tweaking and customizing for the particular performance and power and energy characteristics of that device. But once that's been done, typically by the device manufacturer, you can trust the scheduler. And it will generally start tasks up on a big core so that they start very quickly. And then if they don't need much power, it will migrate them very quickly off to a little core. To adapt very quickly to the task's needs and the changing needs of all the tasks in the system. So generally, you can trust that. Little cores are wonderful. They don't think a little core, because it's energy efficient, doesn't show you high performance. They're actually very high performance devices. Cortex A53 gives you 20% greater performance than a Cortex A9, which you might have used to be using. So they are not low performance. They're very high efficiency. They're still quite high performance devices. And the majority of workloads on a smartphone will run quite happily on one of the little cores. It's only when you need sort of serious performance for short burst acceleration, physics-based effects and so on, the kind of things that you guys do all the time, that you need to start running on a big core. And again, the kernel will handle migrating to those when you need it. There are some things to watch out for. As I said, cluster coherency is really good. It's nice, it's transparent, it's easy, but it's not free. There is a cost to it, partly in terms of time. There is some latency involved if data needs to be moved between two cores in a cluster or between two cores in separate clusters. The bus fabric takes time to do that. It also takes energy to do that. And in some respects, that's a sort of invisible cost to you, but you should be aware of it. So you should be aware of instances where you've got threads that share common data, and if those threads then get scheduled onto different clusters, if you've got one low performance thread and one high performance thread, for instance, one's going to end up on a little core, the other one's going to end up on a big one. If they share data, that data actually has to get shipped all the way out of the clusters, out to the bus fabric, out to that coherent interconnect, where it can be moved across from one cluster to another. So there is a cost with that, and that's something you need to watch out for. This also doesn't apply to any real-time threads that you have in the system. The Linux scheduler recognizes real-time and non-real-time threads, and this big.LITTLE scheduling, this global task scheduling, only works on non-real-time threads. So you need to think quite carefully about the affinity, the core affinity that you use for real-time threads. That can affect the performance of your system. So that's available now. It's easily available, and it gives you, say, fantastic peak performance and very easily attainable high energy efficiency for long battery life, long running workloads and so on. But it's very easy to program for, provided you can decompose your tasks neatly into sensible parallel threads. It also avoids a lot of the thermal constraints on performance because it distributes tasks across multiple cores rather than running multiple threads on a single very big, very hot core. We're spreading tasks out across cores. That effectively spreads them out geographically on the silicon real estate and reduces the energy density of the silicon when it's running. So you run into thermal constraints much less often. So finally, moving on, the third subject that I have, and I've got 8 minutes to introduce you to Neon here. Neon is a fascinating technology. It's a fascinating capability, and it doesn't take much to start leveraging the extra performance this gives you. It's a SIMD architecture, single instruction, multiple data, where we've got multiple data items packed into vector registers, those 128-bit vector registers, and with single instructions, we can carry out parallel operations on pairs of elements held in input registers and generate parallel outputs. It's a standard extension on V8 to the instruction set. It's a standard extension to the register set. And these instructions, which I encourage you to go read about in the manual, I'll show you some small examples, but they operate on these vector registers, these 128-bit vector registers, and we have 32 of those. There they are. You can address them as bytes, half words, single words, double words, or quad words. They go under the official name V0, V1, V2, V3, and so on. So you can see very easily, you can address the bottom half of V0, the bottom 64 bits using the name D0, and you can address the bottom 32 bits of that using S0. But by far the most important capability of these registers is they can carry out SIMD operations. So here is a sort of generalized high-level schematic of how that might happen. We've got two input registers here. They're 128-bit registers. In this case, we're treating each one as an array or vector of 4 32-bit independent data items. So we've got a second register, another 4 items, and we can carry out 4 independent, simultaneous, parallel 32-bit arithmetic operations on those data items and produce, in this case, 4 32-bit results that pack into a single output vector. So you can see the potential for speed and performance increase here just through introducing parallelism at the instruction level. You obviously need to structure the implementation and structure your algorithms so that they vectorize neatly to sort of leverage this capability. But in many cases, that's not difficult. There's a lot of standard, some standard libraries that implement a lot of standard codec functions, display processing functions, and vectorize them neatly for using this architecture. It handles floating point and scalar values. Here's the floating point addition. This is actually, if you look at the syntax here, if I can just unpack that for you, these are the two input registers, V5 and V6, and the .2D means V6 is being treated as two double precision floating point data items. So two 64-bit items make up 128 bits. That fits in a single V register. And we're carrying out two double precision floating point additions and placing the two 64-bit results into V0. So it's in a single instruction, two floating point double precision additions. Here, this is an example here. We're treating V4 in this case as 8 half words, so 8 16-bit quantities. So that single instruction there carries out 8 parallel 16-bit unsigned additions, signed additions, and puts 8 independent results into V0. There's no interaction or overflow between carries and overflow bits with these. Each lane is essentially entirely independent and operates in parallel. Here we've got 8-bit items, which only occupies half of each register. So the effect of this operation here would be to carry out 8-bit additions between V4 and V3, put 8 8-bit results in the bottom half of V0, and actually clear out the top half. So you can use half of these registers. You can use quarter of them as well if you want to. We can also access here single elements of a vector. This is just specifying one single word, in this case word number 2 out of V3, and multiplying each element of V2 by that single element to give 4 results. So you can use scalar and vector operations. You can mix the two. So there's lots of ways of getting access to this extra capability. You can write your own stuff in assembler if you like. It's not that difficult. The most difficult part actually is analyzing your algorithm first and restructuring it, refactoring it in such a way that some of the loops can be unrolled and vectorized and parallelized using these instructions. That's by far the most difficult bit. Once you've done that, writing the assembler is not actually that difficult. However, you can let the compiler do it. And to just give you some pointers about simple changes and transformations you can make to your code to make the job of the compiler in doing this much, much easier. So I've just got 5 stages here of vectorizing a very simple loop that just adds a single scalar item to successive elements of an array. It's trivial stuff. And it does that for an array which is n elements long. They're all integers. Sorry, excuse me. They're all integers. And we've got, I'd say, one element that we're adding on, and we've got a loop count here, which is our loop limit, which is n long. And if you compile that for a Cortex A15, that's 32-bit ARM processor, then you get these instructions here, and you can see there's pressing the wrong one here. There's the main body of the loop, just there. That's just some simple setup. There's the main body of the loop, and here's the control structure at the bottom. Very, very simple. That's not vectorized at all. If you optimize it for performance, now, the compiler has unrolled the loop here, and it's unrolled it by a factor of 2, and there's the loop body down here. And it's simply unrolled it by a factor of 2. But in doing that, it's had to carry out some checks. And the first check is your loop limit 0? Because if so, then we can just skip straight to the end. And the second thing is a bit more important. Is your loop limit odd? Because if your loop limit is odd, then unrolling by a factor of 2 will leave one element hanging off the end. So you have to implement some extra code to handle the odd one, and then you can unroll by a factor of 2 and do all the rest. So you get a little bit of extra code, which allows you to unroll by a factor of 2. So an increase in performance at the expense of space, which is the usual trade-off that you might expect. Now, I can help the compiler a little bit more here, because if I know that my loop limit is actually a power of 2, in this case divisible by 4, I can show the compiler that is true by masking off the bottom 2 bits of it. Now, I've done something potentially a bit dangerous here. I've implemented a piece of code that won't work if my loop limit is not actually divisible by 4. So if this value here that you pass in is not divisible by 4, that loop won't work anymore. But assuming that I stick to my own rules that I've set for myself, and this is always divisible by 4, what that little expression there has told the compiler is you can ignore the bottom 2 bits of n. So you can make the assumption that n is divisible by 4. And you can see what's happened here. This is our loop, which is unrolled by a factor of 2. It's exactly the same as it was on that slide. But you can see that the test for n being odd has disappeared. So we've helped the compiler do the unrolling in a slightly more efficient way, and it's been able to ignore the test because we've told it that n is divisible by 4. Now we can go further than that. If I tell the compiler now to start vectorizing, okay, so this minus vectorize flag says, okay, you can use neon now, go on, do your worst. And you can see that actually the routine explodes, and it takes a bit of time to work out exactly what's gone on here. Right in the middle there is the vectorized version of the loop. And it's been unrolled by a factor of 4 this time, because each of those vload, vadd, vstore, that loads 4 items, carries out 4 additions, and then stores out 4 items. So the loop's been unrolled by a factor of 4. Neat. And you can see it's divided the loop counter here by 2 just by shifting it right 2 bits. That's all neat. That's careful. But what it's had to do here is check whether these 2 pointers refer to overlapping blocks of memory. And if that's the case, then parallelizing in this way at instruction level doesn't work, because as the blocks start to overlap, the load and the store will load elements in the wrong order. So unfortunately, the compiler's had to produce 2 versions of the loop here. It could produce the vector version, which works if A and B arrays do not overlap, but it's also had to output a scalar version that is not vectorized. It's still unrolled by a factor of 4 again, but it started to produce this scalar version of the loop over here, just in case this test for overlapping fails. So you've got an explosion in code size, which is likely, to be honest with you, to be unnecessary, because if A and B overlap, this routine may actually make no sense whatever. So you as the programmer may know that it's pointless to test for A and B overlapping because they never will. So how can you tell the compiler that? The answer is to use the restrict keyword, which is, it was new in C99. It's fairly universal these days. The ARM compiler supports it, as do various other ones. But use the restrict keyword, and what the restrict keyword tells the compiler is you can ignore the possibility that PA and PB refer to overlapping regions of memory. So it essentially allows the compiler to ignore pointer aliasing, which is frees it up hugely. And you can see the difference, the massive difference that makes to the output code, because we can ignore all of this test for overlapping, and we can get rid of that scalar version of the loop instead. And you can see we just go straight to an unrolled by 4 vectorized implementation that uses neon instructions. The key to get that out of the compiler, in this particular case, and these rules apply to many, many other cases, optimize for speed, that's -03 here. Vectorize, that's this flag here. Indicate to the compiler that the number of loop iterations is a power of 2. That allows it to unroll in this case, up to a factor of 4 without having to check for overhanging elements off the end. And it also, and then we tell the compiler that these arrays do not overlap, and then it can ignore having to produce a scalar version of the loop as well. So there's some simple pointers, very simple code transformations that you can do that will allow the C compiler to vectorize for you very, very nicely indeed. And this is, I say, well tried and tested. It works very well. That's all I have to go. I've run out of my time. So hopefully that's a very quick introduction to the world of 64-bit, which is something that you really need to get your head around. That there is performance to be had. There is a huge potential in this big.LITTLE technology for balancing energy efficiency and high performance within a single device, and having that managed essentially automatically, partly by the kernel and partly by the coherency hardware within the clusters themselves. And then neon technology, it's just sitting there there waiting for you to use it. It exists in all V8 cores and the vast majority of V7 cores. It will exist in pretty much any mobile phone or smartphone platform that you care to pick up these days. So it's just there waiting for you to do it. So I haven't had time to tell you much. I would happily tell you much more, but I'm afraid you're going to have to come on one of my training courses to find out. There's some details. If you want to get in touch with me and find out about it, I've got some business cards with me. Do come and get one. My email address is trivially easy to remember, chris.shaw@arm.com. You can remember that. Training@arm.com will also reach me, as will many other things. But please do get in touch if you want to talk about that, and I'll happily introduce you to some more stuff. But thanks for your attention. I hope that was a little bit of an eye-opener to the world of ARM 64-bit. Thank you.
Thanks very much, Chris. Before you run away, Chris, I know still trying to be Batman, did anybody have any questions? Nothing about Bruce Wayne, please. Fantastic. Oh, I haven't got the microphone in my hand, even though there's a chap over there. Could I just take the mic? There you go. Cheers.
Hi there. Hello. It's probably quite a quick one. It's probably a yes/no question. So when you were going through the SIMD instructions, you mentioned that you can do things like add individual bytes and then output and so on, and it would clear the top half of that. Can you output to a different size than the input? So could you add all the bytes, assume overflow, and then just say output words?
Yes, you can. I mean, obviously that applies most often to multiplies. And there are multiply instructions, which are widening instructions that will take, say, 16-bit inputs and produce 32-bit outputs. So you might take 4 16-bit inputs and produce 4 32-bit outputs. Yes, you can do that. There are widening instructions. There are also narrowing instructions as well that produce an output which is narrower than the input. Yeah, the syntax extends to that quite easily. Yes.
Thanks. Thanks very much.
Is that it? You're letting me off really lightly.
Must have been the near perfect talk.
Oh, you say the nicest things, Batman. Thank you.
Right, thanks very much, Chris.